Welcome to session 6 of UNIT-5 in learning the course Design and Analysis of Algorithms. In our previous sessions, we discussed about the branch and bound algorithm design strategy and its applications. We seen the general method of branch and bound algorithm design strategy and two applications we solved using that algorithm design strategy. Those two applications are traveling salesperson problem and 0 by 1 knapsack problem. In this session, we are going to discuss about NP problems, P and NP problems, and also we are going to discuss about Cook's theorem. Now, the main objectives of this session are to understand theory of completeness and P and NP problems and to prove Cook's theorem. The learning outcomes of this session are, by listening this session, one can understand what are P problems, what are NP problems, and able to prove Cook's theorem. The topics that we are going to discuss in this session are basic definitions related to the theory of NP completeness, deterministic and non-deterministic algorithms, P and NP problems, Cook's theorem. Coming to the basic definitions, or the definitions that we are going to discuss. First, we are going to discuss about satisfiability. What is satisfiability? So, for knowing about satisfiability, we need to know what is a literal, what is a formula, and what is a class. In order to know, before going to know what is satisfiability, first we need to know what is a literal, what is a formula, and what is a class. First, let us see. Let x1, x2, x3, so on, xn denotes some Boolean variables. So, here I am representing x1, x2, x3, so on, xn as some Boolean variables. Boolean variables means they takes either 0 or 1. That is the values of those variables. X1 value may be either 0 or 1. X2 value may be either 0 or 1 and so on. Xn value may be either 0 or 1. So, those are Boolean variables. Now, what is a literal? A literal is either a variable or its negation. A variable or its negation is to be called as a literal. That is, for example, x1, it is a literal. Negation of x2, this is a literal. Negation of x1, this is also becomes a literal. So, what is a literal? Either a variable or its negation is called as a literal. Next, a formula. What is a formula? A formula in propositional calculus is an expression that can be constructed using literals and operators such as and, or. Okay, what is a formula? Simply saying a formula can be defined as, or a formula can be constructed by using literals and operators. The operators are nothing but and, or, etc. That is, for example, here I am saying that A is a literal and B is another literal. I am going to write a formula A and B. A and B is a formula. In the same way, negation A is a literal. I am going to write another formula, negation A or B. This is another formula. So, write that. So, if you write literals and operators in a proper manner, we can write a formula. Next, a class. What is a class? A class is a formula with at least one positive literal. What is a class? A class is a formula with at least one positive literal. So, there may be number of negative literals in a formula. If a formula contains at least one positive literal, then we can call that as a class. Suppose, for example, if I am writing a formula as like this, negation A or negation B, is it becomes a class? No, it is not a class, just it is a formula. Since all literals are negative values, here A is a negative value and B is also a negative value since we take a negation for those. So, that is why it is not becomes a class, just it is a formula. Suppose, for example, here I am writing a formula like this, A and negation B. A and negation B. It is a class since there is one positive literal A. Even B may be the negative literal, but there is a positive literal A. So that's why we can call that formula as a class. Right. What is satisfiability? What is satisfiability? The satisfiability problem is to determine if a formula is true for some assignment of truth values to the variable. What is satisfiability means? When we can say a formula is satisfiable, or what is satisfiability problem? The satisfiability problem is to determine if a formula is true for some assignment of truth values. If I assign some truth values to the variables which are present in the formula, if that formula becomes true, then we can call that formula as satisfiable. Okay, let us see the example x1 or x2 or x3. x1 or x2 or x3. And here I am taking another one, negation x1. I am taking another formula, negation x2. This is one formula, this is another formula, and this is another formula. Here I am saying that all these formulas are satisfiable. Now how I can say all these formulas are satisfiable for the given truth values? Here I given the truth values as x1 is false, x2 is false, and x3 is true. Now let us see here this formula, x1 false or x2 false or x3 true. Since in case of OR operation, if any of them is true, the entire formula becomes true. So that's why this becomes true. In the same way, negation x1. So negation x1. x1 is false means negation x1 becomes true. x2 is false. Negation x2 becomes true. Now for the given truth values, since all the three formulas are true, we can say that these three formulas are satisfiable. I hope you all understood what is satisfiability. What is a class, what is a literal, what is a formula, what is class, and what is satisfiability. Coming to the next one, what about various algorithms based on computational time, their computational time, or based on their time complexity. Here we can divide the algorithms into two groups based on their computational times. What are those two groups? So first group consists of problems whose solutions are bounded by the polynomial of some degree. Here these are called as polynomial time algorithms. Polynomial time algorithms. So here we are having two groups of algorithms based on their time complexity. Though out of those two groups, one group is polynomial time algorithms. That is, their time complexity can be represented by a polynomial of some degree. We can represent the time complexity as polynomial of some degree. For example, binary search. It is a polynomial. Sorting and matrix multiplication. So all these are, we can represent. So here the polynomial I can write n power 0 log n. Here the polynomial I can write n power 1 log n. Here I can write the polynomial as n power 2.81. Like that we can represent every term I can represent as a polynomial. So that's why these algorithms are called as polynomial time algorithms. Now group 2 means which are called as non-polynomial time algorithms. Non-polynomial time algorithms. Now here whose time complexity cannot be expressed as a polynomial. So just reverse to the first one. Whose time complexity can be expressed as polynomial, those are called as polynomial time algorithms. Whose time complexity cannot be expressed as a polynomial are called as non-polynomial time algorithms. For example, the traveling salesperson problem and knapsack problem. Here, their time complexities are represented as 2 power n, 2 power n by 2, etc. terms. Since it is not a polynomial, we can write it as the non-polynomial time algorithms. Right. So I hope you understand what are polynomial algorithms, what are non-polynomial time algorithms. Coming to the next one, deterministic and non-deterministic algorithms. What are the deterministic algorithms? What are the non-deterministic algorithms? Let us see. Coming to the first, deterministic algorithms. When the result of every operation is uniquely defined, then it is called as a deterministic algorithm. So, if the result of every operation is uniquely defined, every operation should have a unique solution. Those type of algorithms are called as deterministic algorithms. When the outcome is not uniquely defined, but it is limited to a specific set of possibilities, then it is called as non-deterministic algorithm. So, if we can uniquely define the output, then we can call those as deterministic algorithms. If we cannot uniquely define the output, but it is limited to a set of values, the output is limited to a set of values, those type of algorithms are called as non-deterministic algorithms. Now, let us see. In a deterministic algorithm, for a given particular input, the computer always produce the same output going through the same states. So, in case of deterministic algorithms, if you implement that particular algorithm in a system, for the same input, any number of times if you execute, that gives the same output. So, for one input, if you executed the algorithm for 10 times, that is, for example, here I have an algorithm A, I implemented this algorithm for 10 times and the input I given for this algorithm is n. So, for first time, if I implemented the algorithm with this input, it gives an output x. For the second time also, if the same input is given, it produces the same output. For the third time also, it produces the same output and so on. For the 10th time also, it produces the same output. The output will not be changed. Those type of algorithms are called as deterministic algorithms. And coming to non-deterministic algorithms, for the same input, the compiler may produce different outputs in different runs. That is, I have an algorithm B, I am going to execute this algorithm for 10 times. I am giving the input n. For the first time, it may give an output x. For the second time, it may give an output y. For the third time, it may give an output z. For the fourth time, it may give an output y, and so on. For the 10th time, it may give an output y or z, like that. So, for every iteration, it gives different output. It gives different output. But the set of values which gives the output is limited to a set of values. A specific set of possibilities are there for giving the output. Now, for example, for a deterministic algorithm, here I am giving for I is equal to I from 1 to 9, print I. So, here I am writing a deterministic algorithm which is nothing but for I from 1 to 9, print I. So, how many times if you execute this algorithm, that many times it produces 1 to 9 values. So, here just I want to print I value takes from 1 to 9. If you execute this algorithm 10 times, it produces 10 times this sequence of numbers. 1 to 9 values it prints. So, this is called as a deterministic algorithm. Then what about the example of non-deterministic algorithm? So, here for writing non-deterministic algorithms, we are using 3 terms. What are those 3 terms? Choice, failure, success. Here this is choice, this is failure, and this is success. In writing any non-deterministic algorithm, we need to use these 3 words: choice, failure, success. Now, what about choice? Chooses any value randomly from the set X. Choice is the random function which is used to select a value X from the given set. Now, failure denotes the unsuccessful solution. The failure always denotes the unsuccessful solution. Now, success, this always indicates the successful solution. So, which indicates the current thread termination. That is, its execution is completed. We obtained the solution. The current thread is terminated. Okay. So, now For explaining how to use these three functions in writing a non-deterministic algorithm, here I am taking an example. What is that example means? Search an element x in the given array which contains n elements. Here A is an array which contains n elements. I want to search the presence of or the existence of element x in the given array. So where n greater than or equal to 1, on successful search, return j. If a of j is equal to x, otherwise it returns 0. That is, so if the search is successful, that is the element x is present at some index j, it returns j. Otherwise, it returns 0. If it is unsuccessful search, it returns 0. How to write that algorithm? Let us see that algorithm. J is equal to choice of a comma n. J is equal to choice of a comma n. If a of j is equal to x, then write j success. Now let us see. Here j is a variable. J is a variable. Choice is a random function which selects randomly an element from the given array A which contains n elements. Here A is the given array which contains n elements. Out of these n elements, one element is randomly selected. That selected element index is represented with j. Now, if a of j is equal to x, the search element is equal to a of j. In that case, write j. We are going to return j and we terminate the process by success function. Okay. Else, so if we not found, in all the cases, if we not found, we write it as 0 and we terminate the function with failure. That is, you can observe this. Why we are calling this as non-deterministic algorithm? So, first you implemented the algorithm. First time you implemented the algorithm. So, it selected second value. Randomly it chooses the values. Choice is a random function. It chooses randomly. So, first it selected the second value. The second value may be equal or may not be equal to x. If it is not equal to x, in that case it is terminated with failure. In the second time execution, now you are going to execute the same algorithm for second time with the same input. This choice function may select another element. Since it is a random function, it may select this element. In this case, if that selected element is equal to x, it is terminated with a success function. That is, for the first time I executed, it terminated with failure. In the second time I executed it, it terminated with success. That is, with a set of those two possibilities. Either for all the executions, that is, for first time, if I want to execute that for 10 times, if I want to execute that for 10 times, for first time, it may be terminated with a failure. For second time, it may be terminated with success. Third time, it may be terminated with success. Maybe the random function may select the same value. For the fourth time, it may be terminated with failure. For the fifth time, it may be terminated with success. Sixth time, it may be terminated with failures, and so on. 10th time, it may be terminated with success, like that. Within that possible answers, either success or failure, within those set of possibilities, it produces the output. So that's why we can call this algorithm as a non-deterministic algorithm. So I hope you all understood what are the deterministic algorithms and what are the non-deterministic algorithms. Right. Next we are going for the differences of deterministic and non-deterministic algorithms. So what we learned till now, that itself tells the comparisons between both two. Now you can see now here, for a particular input, the computer will always gives the same output. In case of deterministic algorithms, for a particular input, it always produces the same output. But for non-deterministic algorithms, for a particular input, the computer will give different outputs on different executions. Now, coming to deterministic algorithms, these can be solved in polynomial time. The deterministic algorithms can be solved in polynomial time. That is, their time complexity can be expressed as a polynomial. In case of non-deterministic algorithms, these cannot be solved within polynomial time. That is, their time complexity cannot be expressed as a polynomial. Now, here in case of deterministic algorithms, we can determine the next step of execution. What we are going to execute in the next step, that we can determine. But in case of non-deterministic algorithms, we cannot determine the next step of execution. Due to more than one path the algorithm can take. That is, in the previous example, the choice function, based on the selected value, the algorithm executes. So we cannot predict the selected value since it is the random function. So those type of algorithms are called as non-deterministic algorithms. Next, coming to the next one, we are going to explain. Before going to know, now we are going to know about what are P problems, what are NP problems, what are NP hard problems, and what are NP complete problems, all those things that we are going to discuss. So for discussing about all these things, first we need to know what is reduction. What is reduction? Let us see here what is reduction. Problem A reduces to problem B if and only if A can be solved by a deterministic polynomial time algorithm using a deterministic algorithm that solves B in polynomial time. Now, let us see here. I have a problem A and I have another problem B. I have a problem A and I have another problem B. When I can say problem A reduces to problem B, I can represent the reduction with the symbol this one, alpha. With the symbol alpha, I can represent the reduction. Now, when I can say the problem A reduces to problem B. So, if problem A can be solved by a deterministic algorithm by using which the problem B can be solved. That is, here I have an algorithm, I have a deterministic algorithm. If I can solve the problem A by using this algorithm, if I can solve the problem by using this algorithm. Here, this algorithm is used to solve the problem B. Here, this deterministic algorithm is used to solve B. If I can solve the same, if I can solve the problem A by using same algorithm, by using same algorithm which I used for B, we can say that the problem A is reduces to B. So, I hope you understood what is reduction. If I have an algorithm, if I solve the problem B by using that algorithm, the algorithm is deterministic algorithm, deterministic polynomial time algorithm. If I solve B, the problem B can be solved by using that algorithm, that deterministic algorithm. When I can say problem A is reduces to B, if I can solve the problem A by using a deterministic polynomial time algorithm which is used to solve B, then I can say that problem A is reduces to B. Okay, right. So this is reduction. Then we are going to see what are P problems, what are NP problems, what are NP complete and what are NP hard problems. Here you may think that P means polynomial problems. P means polynomial problems. NP. What are NP problems? You may think of that NP means non-polynomial. But NP means it is not non-polynomial. It is non-deterministic polynomial. NP means non-deterministic polynomial problems. Non-deterministic polynomial problems. Now, what are P problems, what are NP problems, and what are NP hard and NP complete problems? Let us see. P is the class of problems which can be solved by a deterministic polynomial algorithm. P problems means which problems are to be called as P problems? The problems which can be solved by using a deterministic polynomial time algorithm. Those problems are called as P problems. NP problems. What are NP problems? That is non-deterministic polynomial problems. NP means non-deterministic polynomial problems. What are NP problems? The class of decision problems which can be solved by a non-deterministic polynomial time algorithm. NP problems means the class of decision problems. What are decision problems? The problems which gives either yes or no as answers or Boolean values as solutions are called as decision problems. Here, the class of decision problems which can be solved by a non-deterministic polynomial algorithm are called as NP problems. Now, NP hard problems. What are NP hard problems? The class of problems to which every NP problem reduces. That is, every NP problem, that is non-deterministic problem, reduces to some problems. This class of problems are called as NP hard problems. That is, the problems which can be solved by using non-deterministic algorithms. That is, these class of problems can be solved by using some non-deterministic algorithms. The same algorithm can be used to solve these problems also. So that's why we are calling the NP problems which are reduces to NP hard problems. Now, NP complete problems. What are NP complete problems? The class of problems which are NP hard and belongs to NP. The class of problems which are NP hard and also belongs to NP are called as NP complete problems. Now, here you can see the relation between P, NP, NP hard and NP complete. Now, you can write all problems are NP problems. Here you can write all problems are NP problems, and here all these problems are NP hard problems. You can observe that some NP problems may become NP hard. Some NP problems may become NP hard, but all NP hard problems may not become NP problems. Now here some problems within NP, they may become P problems, and here NP complete means the NP hard problems which becomes NP are called as NP complete problems. Here the NP hard problems, that is these problems are NP hard problems. These are also becomes NP problems. Those problems are called as NP complete problems. Now in a deeper way, we want to discuss about the definitions of these one. So here once again I given the definitions for these P, NP, NP hard and NP complete problems. Let us see the definitions once again. What are P problems? The decision problems that can be solved in polynomial time. The decision problems that can be solved in polynomial time are called as P problems. NP problems. The decision problems whose S answer can be verified in polynomial time. Whose S answer. So here I already said you that the decision problem means it gives the solution as either S or no. Okay. Now the NP problems means the decision problems whose S answer can be verified in polynomial time. If it gives S answer, whether it is yes or not, that is we are verifying. That verification is done in polynomial time. Then those problems are called as NP problems. Next, co-NP problems means the decision problems whose no answer can be verified in polynomial time. Some problems may return the solution as no. So here if I can verify that no answer in polynomial time, then we can call those problems as co-NP problems. Next, NP hard problems. What are NP hard problems? A problem is NP hard if and only if a polynomial time algorithm for it implies a polynomial time for every problem in NP. That is, what is NP hard problem means, if I write a polynomial time for an NP hard problem, that should be a polynomial time algorithm for NP problem. I already said you that all NP problems are reduces to NP hard problems, or NP hard problems are reduces to NP problems. That is, if I solve NP problem by using a polynomial time algorithms, the NP hard problems can also be solved by using same polynomial time algorithm. Then we can say NP is reduces to NP hard, or NP hard is reduces to NP. So that's why we can say that NP hard problems are a problem is NP hard if and only if a polynomial time algorithm for it implies a polynomial time algorithm for every problem in NP. Next, NP complete. What is NP complete problem? A problem is NP complete if it is NP hard and is an element of NP. If it is an NP hard, a problem is said to be NP complete means it should be an NP hard problem and it should be an element of NP also. Then only we can call that as a NP complete problem. Now next, what is theory of NP completeness? Here we have a theorem for that NP completeness. What is the theorem means? If any NP complete problem can be solved in polynomial time, then all NP problems can be solved in polynomial time. That is, NP is equal to P. That is, if any NP complete problem can be solved in polynomial time, then all NP problems can be solved in polynomial time. So this is called as theory of NP completeness. So the next one, what we are going to see is Cook's theorem. What is this theorem? What is Cook's theorem? Let us see the Cook's theorem. Cook's theorem states that any NP problem can be converted to satisfiability in polynomial time. Cook's theorem means any NP problem can be converted to satisfiability in polynomial time. So whatever it may be, the NP problem that your satisfiability means it should become true. That is, it should give true answer. It should give true answer. We already seen the definition of satisfiability. When we can say a formula is satisfiable for the given truth values of literals, if it returns a true value, then we can say that formula is satisfiable. Now, what is Cook's theorem statement? NP complete problem. Any NP problem can be converted to satisfiability in polynomial time. That is, for any NP problem, we can get a true answer in polynomial time. That is, we can say all NP problems are satisfiable. Okay, that is Cook's theorem. Now, in another way, we can express the Cook's theorem as, in computational complexity theory, the Cook-Levin theorem. So you may ask it as Cook-Levin theorem also. Cook's theorem or Cook-Levin theorem, both are same. Cook's-Levin theorem, also known as Cook's theorem, which states that Boolean satisfiability problem is NP complete. That is the satisfiability problem. So whatever the problem that you want to solve it as, or you want to show it as satisfiable, that problem comes under NP complete. That problem comes under NP complete. Now, how to prove this Cook's theorem? How to prove this Cook's theorem? Let us see. The proof, let us see the proof. Satisfiability has an NP algorithm. Satisfiability has an NP algorithm. That is, it can be solved with a non-deterministic polynomial time algorithm. So here we can say that satisfiability has an NP algorithm means non-deterministic polynomial time algorithm. For solving any satisfiable problem, we have a non-deterministic polynomial time algorithm. Now, from the definition of NP hard, it is clear that NP hard problems reduces to NP problems and NP problems reduces to NP hard problems. So, we already seen that NP hard problems, from the definition of NP hard problems, we can say that NP hard problems are reduces to NP problems are reduces to NP hard problems. So, we know that all NP complete problems are NP hard. We know that all NP complete problems are NP hard. So, from the above statements, NP problems reduces to NP complete problems. We know that NP problems reduces to NP hard problems. NP problems reduces to NP hard problems. And we also know that NP complete problems are, here all NP complete problems are NP hard problems. All NP complete problems are NP hard problems. So, I can say that NP problems are reduces to NP complete problems from these two. NP problems are reduces to NP hard. NP complete problems are subset of NP hard. So, I can, from those two, I can say that NP problems are reduces to NP complete problems. So, from this one and from this one, we can say that satisfiability is NP complete problem. Satisfiability is NP complete problem. The same thing that I have, satisfiability is in polynomial time. We can say that it can be converted to satisfiability. Any NP problem can be converted to satisfiability in polynomial time. So, that is satisfiability is NP complete problem. So, we proved that Cook's theorem. So, here I hope you all understood the same explanation I given here, the proof, that is the proof of Cook's theorem. So, no need of this one. I hope you all understood what we explained in this session. So I'm going to summarize the concepts what we explained in this session. In this session, we discussed about the basic definitions such as what is a literal, what is a formula, what is class, what is satisfiability, and also we discussed about polynomial time algorithms and non-polynomial time algorithms. We also seen deterministic algorithms and non-deterministic algorithms, and we also seen reducibility. What is reduction? That we seen as the basic concepts. Later we discussed about P, NP, NP hard and NP complete problems. What are P problems? What are NP problems? What are NP hard problems? And what are NP complete problems? What is the relation between all these types of problems that we seen? So later we discussed about Cook's theorem and how to prove Cook's theorem. So to assess yourself here, I given some questions. Please answer these questions. The question is, explain the relation between P and NP problems and prove Cook's theorem. In preparing this presentation, I used the digital content from various public sources. It is used only for educational purpose and not for the commercial purposes. Thank you for listening the session.